Welcome back to Dr. Liu's VCE Chemistry channel. Today, we are breaking down fuel and heat of combustion from the 2025 VCE Chemistry exam. As I go through this, please feel free to correct me if you find any mistakes. All feedback from teachers, parents, and students is greatly appreciated. The correct answer to this question is B. 1. Biomethane, renewable. Biomethane is considered a renewable fuel, often classified as a biofuel. It is produced through the anaerobic digestion of organic matter, such as food waste, agricultural residues, or sewage, by microorganisms. Timescale: the organic matter used to produce biomethane can be replaced or regrown in a very short timeframe, days to years. Carbon cycle: since the carbon in biomethane was recently captured from the atmosphere by plants, its combustion is often viewed as part of a contemporary carbon cycle. 2. Natural gas, non-renewable. Natural gas is a fossil fuel consisting primarily of methane. Timescale: it was formed over millions of years from the remains of ancient marine organisms buried under high pressure and heat. Depletion: because the rate of consumption far exceeds the rate at which it is naturally replenished, it is considered a finite, non-renewable resource. The correct answer is D. To solve this, we need to calculate the energy for the 65.0 G bar first, then scale it up to 100 G, and finally convert the units to joules. 1. Calculate total energy in the 65.0 G bar. Using the standard energy values, often found in the VCE Chemistry data book. Carbohydrates, 17 kJ per G. Proteins, 17 kJ per G. Fats or lipids, 37 kJ per G. 2. Scale to 100 G. The question asks for the energy content per 100 G. We use a simple ratio. 3. Convert to joules, J. Since the options are in joules, J, we multiply by 10 cubed. Conclusion. Looking at the options. 1.3 times 10 to the 6th power J, this is the energy for the 65 G bar, not 100 G. 1.9 times 10 to the 6th power is the closest value to 2.0 times 10 to the 6th power J. Note, depending on whether you use more precise values, 16 kJ per G, or 38 kJ per G, the result remains closest to D. Breaking down the energy profile. In every chemical reaction, energy is involved in two distinct stages. Bond breaking: endothermic energy must be absorbed from the surroundings to break the bonds in the reactants. Bond forming: exothermic energy is released to the surroundings when new bonds form in the products. Why option C is correct. An exothermic reaction is defined by a net release of energy, delta H less than 0. This occurs only when the energy released during bond formation is greater than the energy absorbed during bond breaking. In other words, the cost to break the reactants is lower than the payoff from making the products. A. Incorrect. This describes an endothermic reaction. Exothermic reactions have a net output of energy to the surroundings. B. Incorrect. In an exothermic reaction, the enthalpy of the products is lower than the enthalpy of the reactants, because energy has been lost. D. Incorrect. If breaking the bonds required more energy than what was released, the reaction would be endothermic. The correct answer is C. This question focuses on the concept of a circular economy, which is a key part of the current VCE chemistry and environmental science study designs. Understanding the circular economy. A circular economy aims to eliminate waste and the continual use of resources. Unlike a linear economy, take, make, dispose, a circular system focuses on keeping products and materials in use for as long as possible. Why option C is correct? In the fermentation process to produce bioethanol, carbon dioxide is a major byproduct. By developing a process that captures this waste CO2 and converts it into a useful product, like dry ice, carbonated beverages, or even chemical feedstock, you are closing the loop. This reduces the environmental footprint and maximizes resource efficiency. Analysis of other options. A. Increasing temperature. This is an optimization of reaction rate, kinetics. While it might make the process faster, it doesn't necessarily make it more circular, and might actually increase energy demands. B. Higher yield of ethanol. This is an improvement in efficiency and yield. While beneficial for productivity, it doesn't address the waste aspect of the process as directly as option C. D. Reducing energy consumption. This relates to sustainability and energy efficiency, Green Chemistry Principle 6. While vital for a green process, it focuses on energy input rather than the circular material flow of the chemical byproducts. The correct answer is D. To find the calibration factor, CF, we need to calculate the total electrical energy input, E, and divide it by the change in temperature, delta T. By identifying the molar ratio between glucose, C6H12O6, and carbon dioxide, CO2, you've applied the core principle of stoichiometry to thermochemistry. Key logic check. Carbon balance. Since there are 6 carbons in one glucose molecule, the balanced equations for both combustion and photosynthesis must involve 6 moles of CO2. Energy reciprocity. Because photosynthesis is the exact chemical reverse of combustion in terms of net reactants and products, the magnitude of the enthalpy change, delta H, remains the same, 2840 kilojoules, but the sign flips from negative or releasing to positive or absorbing. The calculation. Using your 1/6 logic. Kim investigated the energy efficiency of 2 different fuels, propane, C3H8, and pure bioethanol, C2H5OH, for heating water. Kim placed a saucepan with 166.0 g of tap water on a portable camp stove and heated it using C3H8. The setup for the experiment is shown below. To write a complete thermochemical equation, you must include states of matter and the enthalpy change, delta H, value. Balance the combustion. Add the enthalpy value. According to the VCE data book, item 13, the molar heat of combustion for propane is 2220 kilojoules per mole. 1 mole propane is completely burned, so the enthalpy value is equal to molar heat of combustion. VCE pitfalls. Missing enthalpy, delta H, failing to include the H value to the right of the equation. A thermochemical equation is incomplete without it. Incorrect sign units. Omitting the negative sign for the exothermic reaction, or failing to include Kj. State of matter errors, SLC. Water, writing H2O, G, instead of H2O, L. At SLC 25C, water is a liquid. Propane, writing C3H8, L, instead of C3H8G. Propane is a gas at SLC. Stoichiometric balancing. The error, incorrectly balancing the oxygen, O2 molecules. The fix, follow the CHO method, carbon, then hydrogen, then oxygen. 3CO2, to match 3 carbons in C3H8. 4H2O, to match 8 hydrogens in C3H8. Total oxygen atoms on the right equals 10, 6 from 3CO2 plus 4 from 4H2O. Therefore, 5 O2 are required. Note, if a student uses fractional coefficients, e.g., if they were balancing for 1 mole of a different fuel, the delta H value must be scaled accordingly. However, for propane, whole numbers are standard. To find the total energy released, we first find the number of moles, N, of propane burned and then multiply by the molar enthalpy. Step 1. Calculate moles of propane, C3H8. Using N equals m. N C3H8 equals 9.0 g of 44.0 g per mole equals 0.2045 moles. Step 2. Calculate energy released. Energy, Q, equals N times delta HC. Q equals 0.2045 moles times 2,220 kilojoules per mole equals 454.09 kJ. Final answer. The amount of energy released is 4.5 times 10 squared kJ, rounded to two significant figures, matching the 9.0 g provided in the prompt. This is the core of the practical investigation. To solve these, we'll use the experimental data from the previous images. Mass of water, m 166.0 g. Initial temp, T 24.1 degrees Celsius. Final temp, TF 90.1 degrees Celsius. Energy released by propane, from part B 454 kilojoules. C.I. Calculate the energy absorbed by the water. We use the specific heat capacity formula. Maker 1, find delta T. Calculate Q in joules and convert to kJ. The specific heat capacity of water is 4.18 J per G per degree C, from the data book. C2. Determine the overall energy efficiency. Efficiency is the ratio of useful energy, absorbed by water, to the total energy available or released by fuel. This is a significant 4-mark question that requires several steps: calculating the moles of each reactant, identifying the limiting reactant, and then finding the mass of the leftover, excess, reactant. Step 1. Calculate the amount, moles, of C3H8. We have 9.0 g of propane, m equals 44.0 g per mole. Step 2. Calculate the amount, moles, of O2. The container has a volume of 0.125 cubic m, which is 125 L. Volume of oxygen, only 21% of that volume is oxygen. Moles of oxygen, at SLC, the molar volume, Vm, is 24.8 L per mole. Step 3. Determine the limiting reactant. From the balanced equation in part A. The ratio of propane to oxygen is 1:5. To react all 0.2045 moles of propane, we need 0.2045 times 5 is equal to 1.0225 mole of O2. We have 1.0585 moles of O2. Since we have more oxygen than required, C3H8 is the limiting reactant, and O2 is in excess. Step 4. Calculate the mass of excess oxygen. Mark 1. Finding moles of propane, 0.205. Mark 1. Finding moles of oxygen, 1.06, using molar volume at SLC. Mark 1. Correctly identifying the limiting reactant using the 1:5 ratio. Mark 1. Final mass of excess oxygen with correct units. The specific energy content of ethanol, approximate 29.7 kilojoules per g, is significantly lower than that of propane, approximate 50.5 kilojoules per g. This is because ethanol is already partially oxidized due to the presence of the hydroxyl group in its structure, resulting in a lower proportion of carbon and hydrogen by mass. Consequently, a larger mass of ethanol must be combusted to release the same total amount of thermal energy as propane. In a scientific and VCE context, while energy content is often used as a general descriptive term, specific energy is the precise technical term required for mass-based comparisons. Here is the breakdown of the differences. 1. Terminology and precision. Energy content, general term. This is a broad, non-specific umbrella term. It refers to the amount of energy stored in a substance, but doesn't strictly define the units. It could refer to energy per mole, per gram, or even per serving in food chemistry. Specific energy, technical term. This is a scientifically rigorous term, defined specifically as the energy per unit mass. In the SI system and VCE chemistry, it is almost always expressed in kJ per g or mJ per kilogram. 2. Why specific energy is the academic choice. When you are explaining question 1e, the mass difference between ethanol and propane, specific energy is the superior term for two reasons. Mass-centric logic, the question provides data in grams, 9.0 g vs 15.3 g. By using specific energy, you are directly addressing the energy-to-mass ratio, which is the heart of the problem. Avoids molar confusion. As the official VCE report hints, students often confuse molar enthalpy delta H with the energy released in a practical setting. Specific energy forces the focus onto the mass of the fuel, making the partial oxidation argument, where oxygen adds mass, but no energy, much clearer. 3.0 Examiner's Report, Common Pitfalls. Pitfall 1, Vague references to bond enthalpies. Avoid using bond enthalpies as a standalone explanation. The warning, examiners state that simply mentioning bond strength is insufficient without a full Hess's law calculation. This is considered beyond the scope of the expected response for this specific comparison. Pitfall 2, confusing molar enthalpy with specific energy. Failure to distinguish between delta H, kJ per mole, and specific energy, kJg. The warning, because the question provides data in grams, the comparison must be made on a per gram basis. A common error is providing the molar enthalpy value from the data book without converting it to reflect the mass used in the experiment. One key concept: specific energy versus structural oxidation. Definition: specific energy, kJ per g, is the precise term for energy per unit mass. The Y propane has a higher specific energy than ethanol. Structural reason: ethanol is partially oxidized due to its hydroxyl OH group. The oxygen adds dead mass that does not contribute to the enthalpy of combustion. 2. Calculations and calorimetry. Thermochemical equations must include states of matter at SLC, water is liquid, and delta H with the correct sign for combustion. Calibration factor, CF calculated as CF equals Vit delta T units, J per degree C. Efficiency is the ratio of useful energy absorbed by water to the total energy. 3. Sustainability and circularity. Renewability, defined by the timescale of the carbon cycle, short term for biofuels versus millions of years for fossil fuels. Circular economy, focused on waste valorization, e.g., capturing CO2 from fermentation to use in greenhouses, rather than just increasing thermal efficiency. If you need my help, please add me on WeChat or WhatsApp and send me an email. Thanks for your attention. Please note Dr. Liu's VCE Physics channel, Dr. Liu's VCE Chemistry channel, and Dr. Liu's VCE Biology channel.